This video is about the in-class quiz on Chapter 7. Let's look at number 1. Consider a hollow metal box. So, let's see what we got. Got a hollow metal box. Completely enclosing a region of vacuum, so absolutely nothing inside the box. The box is in the shape of a cube of this size. Consider the metal to be a perfect conductor. The person puts some charge on the box. So they charge the box, and then they measure the electric potential to be 28 volts relative to 0 volts at infinity. At this point right here, and what would the potential at the corner of a box be? Okay, if the box is a perfect conductor, then everywhere in and on the box, the electric field, so inside the box and inside the material of which the box is made, the electric field is 0. So that means that the work done in moving a charged particle from one point on the box to another point on the box is going to be equal to 0, and hence the electric potential at all points on the box is 0. So the electric potential at all points on the surface and within a perfectly conducting material, the surface of and in a perfectly conducting material, they're all going to be at the same value. So if the electric potential is 28 volts at one point, then it's 28 volts everywhere. That's really enough that you can store it away. I guess some conceptual understanding of it there, but for a perfect conductor, the electric potential everywhere in and on the perfect conductor has one and the same value. Alright, now let's look at number 2. Box, same kind of box. What would the potential at the center of the inside of the box be? Okay, everywhere in and on a perfect conductor, the electric field is 0. So to take a charged particle from a point on the surface to a point inside would require 0 work. 0 work would be done by the electric field because the electric field is 0. And if we calculate the work done as a change in potential energy, that means there can be 0 difference in the electric potential value at the surface and at the center, and hence no change corresponds to 28 volts. If it's 28 volts on the surface, it's 28 volts everywhere inside and on at any point on the surface in the material inside the box. So 28 volts would be the potential at the center of the inside of the box. Now let's take a look at this third one. Same kind of thing. Would an electron have a higher potential energy close to the box or far away from the box? Now, at the box, the electric potential is 28 volts, and the electric potential energy of the electron is going to be the charge of the electron times the electric potential. So at the surface, it would have an electric potential energy, this is negative, of minus 28 electron volts. That's the electric potential that the electron would have, and we recognize it's really the energy of the system, but our language usage is that we, for accounting purposes, we attribute the energy to the electron, so calling it the energy of the electron is perfectly okay in this context. So would an electron have a higher potential energy? So at the surface of the box, the closest you can get to the box, it's got minus 28 volts, and then the further away from the box you get, the smaller the magnitude of the electric potential energy. And in fact, if the electron is an infinite distance away, the electric potential energy would be 0 volts. So the highest possible value is 0 volts, the lowest possible value is minus 28 volts, and the closer you are to the box, the closer you are to that minus 28 volts, the closer you are, the lower. So would an electron have a higher potential energy close to the box or far away from the box? Far away from the box. So up to the point where it's an infinite distance away from the box, where it would have 0 potential energy, the highest possible value of potential energy, 28 volts, higher than the minimum possible value, which is minus 28 volts. Alright, that's it for this video in which I go over the in-class quiz on Chapter 7.